두 번째 연사로서는 미국 해군연구소의 델 맥모러 박사님께서 단일 이벤트 효과 테스트를 위한 펄스 레이저 기술의 기초에 대한 발표를 진행하시도록 하겠습니다. 맥모러 박사님께서는 플로리다 주립대학교에서 물리화학 박사 학위를 취득하셨으며 박사 학위 후 토론토 대학교에서 펠로십을 마친 이후에 1998년부터 워싱턴 DC의 해군연구소에서 근무하셨습니다. 그의 최근 연구 분야는 분자간 역학 및 액체, 용액, 유리의 들뜬 상태의 광물리학적 과정을 조사하기 위해 초고속 비선형 광합 분석 기법을 사용하는 것과 마이크로 전자장치와 복잡한 회로에서의 단일 이벤트 현상을 시뮬레이션하기 위한 레이저 기반 방법론의 개발, 특성화 및 적용을 연구하고 계십니다. 오늘의 발표에서는 직접 회로에서 방사선에 의한 단일 이벤트 효과를 연구하기 위한 펄스 레이저 사용에 대해서 설명하시면서 일반적인 고장 메커니즘과 근본적인 레이저 테스트 방법에 대해서 제시합니다. 메모리의 단일 이벤트 업셋을 연구하기 위해 펄스 레이저를 사용하는 장점을 설명하시기 위한 샘플 결과 또한 제공됩니다. 맥모로 박사님을 환영해 주시길 바랍니다.
Good morning. This is Dale McMorrow from Naval Research Lab. Today, I'm going to be talking about fundamentals of the pulse laser technique for single event effects testing. First, I'd like to thank the organizers for inviting me to give this presentation. I think it's quite interesting. I noticed the name change from Advanced Semiconductor Safety Innovation Conference from automotive to advanced. I think that's quite interesting. I've gone back and looked at some of the programs for past years, and I see that this particular meeting has been moving in that direction, diversifying more away from purely automotive to other radiation effects types areas. So I think it's very interesting. The subtitle for this particular meeting is Advanced Radiation Testing, Data Analysis, and Validation Examples. So that's what I'm going to talk about today. The goals of this presentation. First of all, I'd like to give a basic understanding of the pulse laser single event effects approach. And then I'd like to give a general understanding of its various uses and applications, what we can use it for, why it's useful, et cetera, et cetera. Okay, before I really get into anything, we should start with a definition of single event effects. A single event effect is a disturbance to the normal operation of a circuit caused by the passage of a single ion through or near a sensitive node in the circuit. And these single event effects can be either destructive or non-destructive. And there's a table on this slide showing the various types. There are others as well. There's quite a long list, and there are new ones being discovered all the time. But it's quite informative to look at the different types, especially for space applications. Destructive SEEs are incredibly important because when you have a satellite in orbit, you can't go in and repair something. Similarly, and I'm not an expert in the field, but in the automotive field, you also can't handle errors that disrupt the activity. I'm thinking in particular of self-driving cars, and I know that's where the field is going. So these types of events are very relevant to both fields. Start with a little background. In terms of what we typically deal with in terms of the space radiation environment, we deal with various phenomena. You've got the solar wind, and that involves the 12, 13-year solar cycle, solar flares, coronal mass ejections, the trapped radiation belts, the Van Allen belts, which consists of protons and electrons, and of course, galactic cosmic rays. You've got this very beautiful artist's depiction. I believe this was a Japanese artist, but I apologize that I've lost the citation for that. But it gives a very nice picture, and I'll show a bit more in a second. Very basic. We all know that the internal magnetic field of the Earth is approximated as a dipole field, as shown schematically here. And then this is what traps the particles in the Van Allen radiation belts. And this is an artist's depiction of what the radiation belts look like. You've got the inner belts, which are dominated by protons, or the inner belt, and the outer belts that are dominated by electrons. And they go out to geo orbits. Okay, this picture kind of builds on the previous one, and it shows how the solar wind, the charged particles in the solar wind that emanate from the sun, distort the Earth's magnetic field and give you that distorted picture that you saw in the earlier figure and in this thing, in this particular figure. Okay, and there's a lot. I mean, this is a whole field into itself, and there's a lot of very interesting stuff. But this, I think, is a very unique and interesting example. The magnetic axis of the Earth is not aligned with the rotational axis, and it's also shifted. So it's tilted and shifted, and this has a very significant practical effect on the belts. And as you can see in this schematic diagram on the left here, there's an area where the belts dip close to the Earth's surface. That area is referred to the South Atlantic anomaly. On the figure on the right shows actual SEU data from a memory on an ESA satellite, UOSat. I forget the year of this, but you see the high concentration of errors detected in the region over basically northern Argentina, Brazil. This is where the South Atlantic anomaly exists. You also see higher concentrations near the poles, and that's because the belts dip down there, or the magnetic fields dip down, and other things go on there. But anyway, this is just an interesting example of the type of thing that we deal with in space systems. Okay, so this community, as I understand it, is more interested in terrestrial effects. Space, I would call it terrestrial and avionic. So you're dealing with automotive, you're dealing with commercial airplanes, of course, military aircraft, et cetera. And the primary threat in terms of single event effects for those entities is neutrons. And neutrons are created by a cascade of particles that arise from a galactic cosmic ray arriving from deep space, interacting with atoms in the atmosphere, just creating this cascade of particles as is shown in this figure. Now, there's a lot going on here, and I'm not going to go through it all. But in the end, what we end up with is neutron concentrations that vary as a function of the distance from the surface of the Earth. So you get a lot higher neutron concentrations up in the higher atmosphere, and it's lower near sea level. Okay, but these are the kind of things that I assume this community, the computing community, the server community, et cetera, have been dealing with for quite some time. Okay, so moving into pulsed laser single event effects. Basically, the particles that I've described interact, the energetic charged particles interact with the semiconductors and insulators that make up integrated circuits. They liberate electrons, creating a dense electron hole plasma, as is shown schematically in this figure. This figure is for an indium phosphide HIMP, but it could be any device. The same type of thing occurs. Now, for neutrons, the mechanism is different. And I don't have a slide for neutrons, but what neutrons do is they collide with particles of the semiconductor or atoms in the semiconductor lattice, lead into nuclear reaction. And you have displacements and you have spallation products that it's those products, those charged products that give rise to the charge that in effect leads to a single event in a particular circuit. Okay, so pulsed laser single event effects. In particular, the point that I like to make that I think is most important for orienting yourself as to what this technique is used for is that it is a tool for injecting charge in a well-defined manner into semiconductor, microelectronic, and nanoelectronic structures. The key aspect of this is spatial selectivity. You can focus down to a spot depending on the wavelength, well below a micron. And you can use that as a tool for injecting charge pretty much anywhere in a semiconductor device that you can gain access to. Okay, so some examples of what it's used for, and I've highlighted a few, but I'll go down the list. Primary, the primary function, and this is where the field started, is sensitive node identification and characterization. As I said, you can pinpoint your charge injection, and you can understand what happens when you inject charge in that particular point. Okay, one step further from that is mapping. If you can locate the spot, then you can map all out the area around it, and you can get these very nice SEE maps. Other applications, digital single event transient characterization and mitigation. This was a really big deal back around 2005, in the late 2000s. And we did a fair amount of work. I'll show an example of that. Laser-induced latch-up screening and mitigation is an active area of research right now. And analog single event transient screening is also an active area of research right now. Hardened circuit verification, whether it's RHBD, which is radiation hardened by design, or RHBP, radiation hardened by process. These are areas where we and this technique assist in educating and bringing along students. We work a lot with graduate students from various universities because the pulse laser is a tool for injecting charge, and they can test their RHBD circuits. And we get a lot of that going on. Fault injection is something that I believe the automotive industry is quite interested in. Various industrial industries have adopted this technique over the years, and that field is separate from the laser single event effects field, and they've kind of evolved in parallel, but there's a lot of cross pollination between them. Dynamic SEE testing with lasers, you can do timing that you can't do otherwise. An area that's become especially important recently is experimental test setup and verification. Before you go to a particle accelerator facility, you can bring your test setup to the lab, and we can evaluate and make sure everything's working, so you don't waste time when you're at the accelerator. Complex circuit evaluation, error signature identification is also a big deal, especially for some of the systems on a chip, FPGAs, et cetera. And then, of course, basic mechanisms, which is pretty much where I got started in the field. Okay, one example, real quick. This is a phase lock loop charge pump circuit. This is some work that Daniel Lovelace did. He was a Vanderbilt graduate student. It was published in 2010. It was part of his PhD research. And what this shows is an SET error map that we obtained by scanning the laser. In this case, we were using backside through wafer 2-photon absorption. I'll get back into that. But basically, by scanning the laser, a fixed laser pulse energy, or scanning the position, I should say, the technique identifies the various single event transients. The one example that's picked off here, the raw data is shown in the top panel on the left. In the middle, it's plotted as a function of frequency and a frequency displacement, I guess you would call it. And the bottom one is plotting the phase displacement. But basically, that's what your single event transient looks like. In this particular case, you can see that it's about 400 nanoseconds long. Okay, so that can cause significant disruption in a circuit. Okay, here's one more example. This is something quite similar. This is a scan, an SET scan. In this case, though, it's a gallium nitride hemp, and this is just a single transistor. So you can see the scale. It's about 25 microns on the side. And this is parallel. The gate is running vertical on the left-hand side of this figure. And what you see on the right are transients at different locations, or transients at a given location. And on the left, you see these hotspots that are kind of unique. And we're still trying to fully understand them, but it seems to be areas of higher density of defects that's giving rise to these hotspots and giving rise to larger transients. Okay, that's the type of stuff we can do. Okay, historical. 1991, which was not long after I got into the field, there were basically 3 labs doing pulse laser SEE. There was our lab at NRL. There was Martin Marietta, where Steve Buckner was working at the time. And then there was aerospace out in Los Angeles, El Segundo. By 2005, there's a few more people involved. The Europeans picked up the laser technique in a big way. The Russians and the Japanese started dabbling in it. Okay, and then by 2019, I've got this map here, which I am certain is not complete, because we now have 3 commercial companies building and selling pulse laser SEE test setups, and they don't tell me, or they don't tell us who they're selling them to. And unless someone goes out and publishes a paper or does a presentation at a conference or tells us that they have this system and they're working on it, then we don't know it's there, because these things are not advertised. But as you can see, by 2019, you now have laser SEE labs in the US, Intel, Los Alamos, JPL, Vanderbilt University up in Canada, all over Europe, TRAD, CNES in particular, MBDA in the UK. And then the Russian labs are still there. You've got new labs in China, Singapore, and in Japan. So the technique is now much more is now quite widespread, and it's growing regularly. Okay, this is what our experimental setup looks like for one particular setup. This was a 45 nanometer RHBD test on a PLL design. And what you see is, you see the microscope objective there in red. Above that is a beam tube where the beam is propagates, and we pick it off to image the device as well as illuminate the device so we can see it. You can see the board on a massive XYZ stage. The reason for the massive stage is because mechanical stability is a big deal when you're focusing spots down below a micron. Here's another example. This is a high-speed test on a high-speed printed circuit board that was designed, in this particular case, by the students at Georgia Tech. You can see the high-speed cables coming off. I believe this was a SIGI HBT test, but I'm not so sure. And you can't see anything because it's flipped upside down and we're going through the backside, through that hole in the back. But that's another example of what the test setup looks like, and it varies for any given test, any given board. You have to adapt to whatever the situation is. One of the issues with pulse laser testing is that you have to get light into the device. And there are challenges. This slide is labeled cross-section of a modern device. Well, this was a modern device probably 20 years ago. But you see 5 layers of metal, you see tungsten plugs, you see the device layer, the circuit layer way down at the bottom. And basically, as technology evolved, once we got to about quarter micron technology node, it became difficult to do laser experiments from the top side. And to basically get the light through these this metal. I mean, there were exceptions, and we were successful in some cases. But as technology advanced, it became more and more difficult, and it became essential to come in through the backside. So we developed a technique at NRL to where we could go through the backside of the wafer using nonlinear absorption, 2-photon absorption, basically. And so we were able to overcome that, and that I think was about 2003, and we did that out of necessity for a program that really had no other way to get to their device and interrogate it. So I'll talk more about this as we move forward, but that's the basic idea. And this slide shows the optical absorption spectrum of silicon. Typical wavelengths for pulse laser SEE testing are shown. 600 nanometers is more or less where we started. 800 nanometers is very convenient for various reasons. A lot of work has been done at 1.06 micron because you're way out on the band edge and you get a very long penetration depth. And then for the 2-photon work, you work in the transparency region, which is below the band gap. We started working at 1.26 micron, as is indicated here, and you can pretty much work anywhere to the right of that. And you don't want to get too close to the band edge because then you start getting interference from various things. But basically, we chose that wavelength because there was a minimum in the free carrier absorption spectrum, and we thought that was important, so we went with it. And here's the idea. On the left, I show a schematic example of single photon absorption. Basically, a single photon is absorbed by the material, and it creates a single electron pair, as is illustrated here. For 2-photon absorption, it's quite analogous, except that 2 photons are interacting with the material simultaneously, and then they create a single electron hole pair. Now, in this particular example, the electron ends up in basically the same energy state that in both cases. In the 2-photon case, the photon energy is basically half of that in the single photon case in the example I show here. So now we get back to this diagram, the absorption spectrum of silicon, and I've added the wavelengths that are now typically used. As this field has evolved, people started doing tests at 1.3 microns and then also at 1.55. Now, 1.55 is convenient because that's a telecom wavelength. So it's not surprising that people migrated out there. And we started doing some tests out there too for other reasons, which is really pretty much beyond the scope of this talk. But all of these wavelengths or any wavelength in this region can be used for 2-photon absorption in silicon. Now, if you go to different materials, of course, you have different absorption spectra, and you have to adjust for that. For like gallium nitride, the wide band gaps, you need something that's larger than half of the band gap. So you typically, when we do those, you might be working around 600 nanometers for a 2-photon absorption and go into the UV for a single photon absorption study. Okay, this is a very crude diagram of what the experimental setup looks like. The pulse is arrives from the right there. It goes through a polarizer waveplate combination to adjust the energy level. It goes through a spatial filter and a collimator. There's a lot more details in here now as the technique has evolved, but this is basic. We have a beam splitter to detect the pulse energy, an autocorrelator to detect the pulse width, to measure the pulse width. Then we have what's called a nonlinear photodiode, where we use the 3 of these detectors together to do dosimetry, to really quantitatively characterize what's going on in the laser pulse. And then the beam is sent around through a microscope objective onto your DUT. Since we're talking about two-photon absorption, we have to deal with nonlinear beam propagation. Nonlinear beam propagation is basically described by these three coupled equations. Now, these are really only valid in optically thin media. We don't very often work with optically thin media, so these generally don't apply. You have to do a more complex calculation. But these provide a very good way of visualizing what's going on. So the carrier generation equation is the most important equation because that's where carriers are generated. So what we have here is two terms. The first term is a linear term, which describes single photon absorption. It's proportional to the absorption coefficient and to the pulse irradiance. The second term is the two photon term. It's proportional to the two photon absorption coefficient, beta 2, and quadratic. It varies quadratically with the irradiance. Okay. Now, the irradiance equation basically describes the losses the beam experiences as it propagates through the material. So you got three loss terms there. The first two are just the linear, or the linear and the single photon and the two photon terms from the carrier generation equation. There's an additional term there that arises from free carrier absorption. I mentioned that a bit earlier, but basically this is the loss due to absorption by carriers that have already been excited into the conduction band. They don't have to be excited. They can be there automatically by doping, for example. But that's the free carrier absorption term. Phase equation is also very important when it comes to understanding what's going on and being able to model your pulse propagation. And here you've got two terms that are of significance. N2 is the nonlinear index of refraction, and sigma FCR is the free carrier refractive term. These are shown in the next slide schematically. So this kind of illustrates those equations. The top left shows two photon absorption. Basically, the light goes in and it comes out with less intensity, fewer photons. You've got absorption going on. Okay. Below that, you have the two phase terms, the nonlinear refraction and free carrier refraction. Nonlinear refraction has a positive, is a positive number in silicon, and so it leads to self-focusing. The beam will focus upon itself. Free carrier reaction is just the opposite. It's a negative number, and so it leads to self-defocusing. And so you can see immediately how these can affect an intense optical pulse as it's propagating through a semiconductor material. If you get into the intensity levels, the irradiance levels that these effects start kicking in, they're going to change the shape of your beam. And then the free carrier absorption is shown on the right. You have two photon absorption creates carriers in the conduction band. Those carriers can then be excited to higher levels. You don't get any new carriers, so therefore it's a loss term. You're losing photons. You're not creating new carriers, but what it does is it generates heat, and it also generates the free carrier refraction down below. I mean, I say heat because when you excite carriers, they relax, and they relax to the bottom of the conduction band, and in doing so, they give off photons and give off heat. Okay, so circling back now. This is the carrier generation equation again. Let's focus on it for a second. It shows the linear and the nonlinear terms, single photon absorption, two photon absorption. If we neglect the two photon absorption term, you solve the equation, you get what is well known as the Beer-Lambert law, and it's shown here. Key aspect of it is that two key aspects. One is that it's linear in the irradiance, I of t, and it has an exponentially decaying aspect. Basically, you lose photons as you propagate into the material, and that gives rise to the exponential decay. Okay, this is what it looks like for two different wavelengths, 590 nanometer, 800 nanometer. you can see the exponential decay. You can see that the light shown in red, the intensity of the pulse basically goes away as it propagates into the material. And 800 nanometer, you get a longer penetration depth because you're farther down the band gap. Okay, now if we look just at the two photon term, the solution is shown in the bottom. Basically, what you notice especially is that the exponential decaying term is absent. And this is a key feature. The other key feature is that it's quadratic in the irradiance. And what that gives you basically is a situation that looks like this. When you focus the beam into the material, two photon generation is most efficient in the high irradiance region near the focus of the beam. And this is because of the I-squared dependence and the lack of exponential attenuation. Because of this characteristic, we can inject carriers at any depth in the material. And so the experimental parameters that are important is that basically, put it differently, the experimental parameters that give you the very high photon densities you need for this phenomenon to be efficient are a tight focus, a short pulse, and a high pulse energy. And we can play with all of those. They're parameters that we can adjust. Okay, just to clarify, what this chart shows is the correct aspect ratio for what I show on the left. You know, we plot this thing this way because it fits on the plot. It's convenient. It's a good sized rectangle. But in reality, what we've got is this elongated distribution of charge that's shown on the right. Okay, modeling these things is not trivial. We started working on this several years ago. Other groups have worked on it, and this chart kind of shows some of the work that's been done to date. I'm not going to go through all this, but the figures that I'm showing in this presentation are generated with NLO BPM, which is a program that was originally developed by Eric Van Stralen's group at the University of Central Florida, one of the premier nonlinear optical groups in the country, in the world. And it was passed on to us, and we've been using it for this work. And then you've got the other work. Lumerical is a commercial code that Vanderbilt it has been using, adapted for these types of studies. Okay, an example. This is an old example, but it's kind of fun. Three-dimensional mapping of SEE sensitivity based on what I just said. Okay, this is a top view and a side view, cross-section view of an LM124, one transistor, Q20 of an LM124 operational amplifier, okay? So if we inject charge into this device, you get transients. Or if we inject charge into this transistor of this device, you get transients that look like this. And when you're just injecting a little bit of charge into the surface, you get a transient that looks like this. And these are actual measurements, by the way. As you move the beam deeper into the device, that transient gets larger. As you move down deeper, it starts to switch polarity. And this continues. As more charge is deposited in the device, the transient gets larger. Eventually, it saturates. And then eventually, once you start depositing charge way below the active region of the device, it goes away. Okay, so that's interesting and it's fun. But what it illustrates is the fact that with two photon absorption, you can focus your spot anywhere in the device you want, X, Y, or Z. Now, the Z dependence is really only important for older technologies like this. It's not going to do you any good in, say, a fully depleted SOI device, or any SOI device for that matter. It's going to be of limited value for bulk CMOS and stuff, except it might be important in latch-up studies or something like that. But anyway, it's an interesting example that illustrates the principle. Okay, getting into actual testing. At the top, it states that the primary experimental constraint is optical access to the silicon. And this is key because visible light will not go through metal. So you have packaging issues and you have metallization issues. You have in the middle, in the green there, you have dummies that in the more recent technologies, they're called dummies that the foundries put in to aid in planarization, to have a uniform metal coverage, so they don't get dips and divots when they start polishing. You can see on the right, you see an interesting package. But yeah, so these are all issues that are very important. And if you're going to do pulse laser testing, you need to be aware and you need to know how to deal with them. So front side versus back side. I've talked about this already. On the left, we show what I call front side. We also call it top side. And I apologize for the confusion. We haven't been very consistent in the field. But this is where you come in from the top, the metallization layers, the circuit layers, et cetera, as is shown on the left. In contrast, if you go through the wafer, we call that backside. We also call it through wafer. You can access the circuit layers without going through the metallization of the processing, the back end of the line, et cetera. And you can see the difference in the photos at the top. You can see the one on the right is a flip chip device where you see basically the wafer. And these are really, really nice for laser testing because we can go right through that wafer without a big problem. Here's one example comparing front side and back side at 1064. Now, I've been talking about using 2-photon absorption for backside testing. You can also use long wavelengths that are just near the band edge, and 1064 is a common one. It's got a several hundred micron penetration depth. I think it's about 700, 800 nanometers at 1064 in silicon. And so you can do front side and backside comparisons that way. And that's what's shown here. This is also the LM124. This was work done by Vincent Pouget's group in Bordeaux at the time, back in 2001. But you can see where for top side, the metal interferes, and from the back side, you get very nice maps of the sensitive areas of the device. Now, just to be clear though, top side irradiation has a lot of benefits as well. And it's not going to give you the pretty picture like on the right, but there's a tremendous amount of information. And a lot of work was done for many years using just top-side irradiation. Okay, additional concerns. These basically, laser testing is different from heavy ion testing. This is not particularly relevant, I don't think, to the automotive community. But for the radiation community, it is relevant because lots of the things you learn in testing at particle accelerators can lead you down the wrong path with pulse laser testing. So a bunch of things are listed on this slide. The biggest one in the middle, optical access to the silicon I just talked about. Angle of incidence is a question we always get. You usually don't deal with it. Mechanical stability is a big deal. And then at the very bottom, optical calibration and validation is essential for many studies. Early on, it wasn't, and we didn't really care. We didn't need that, but the more we've moved forward in the field, the more we need quantitative numbers. Okay, so a few examples here. Single event mapping in an SRAM cell. This is a very simple design. It's a test structure that was specifically designed for laser testing by Vincent Pouget and his group in Bordeaux. Now at Montpellier, but back then he was at Bordeaux, and this is what the SRAM looks like: 0.8 micron by CMOS technology. Here's the way it works. Basically, you set up a grid and you start scanning. You scan row by row, you get an upset, you save it, catalog it, keep going, catalog all your upsets, increase the laser pulse energy, scan again, increase the laser pulse energy, scan again, and then in the end, you get a map. You can combine all that data and you get a nice map like shown on the lower right. I'll show a better picture of that in a second. But here's what it looks like when you're doing a real experiment. low pulse energy, you see some upsets. Increase the energy, you see more as you increase the energy, and then eventually you get these very nice big spots. Now, the laser spot is not changing here, basically, but what's happening is you're depositing high levels of charge farther away that are sensitive enough to diffuse to the sensitive node and cause an upset. So that's what you're seeing there. And this is what it looks like when you combine all those into a single picture, which is a very, very nice picture. You can plot this data differently. You can plot it in terms of a cross-section. This looks very much like a heavy ion cross-section you might see for an accelerator measurement. It's similar, it's related, but it's not the same. And I don't have time to really go into all those details. But anyway, it's an interesting way to look at the data. Spatial selectivity. I've got a few examples here. Laser-induced latch-up evaluation and mitigation in CMOS devices. This is an interesting example. Everybody knows GPS. GPS-2 satellite was about to launch back in 2000. And what they found at the last minute, the NASA team did, that it had a latch-up sensitivity, okay? And this is unacceptable. And they were very possibly going to scrub the launch. Anybody that's launched a satellite knows that scrubbing a launch is an extremely expensive proposition, and they don't want to do that. So they brought the part, the suspect part, to the NRL laser lab, and we were able to localize the latch up to a very small region, or observe that the latch up was localized to a very small region, such that redesign was possible. So Boeing redesigned the part, National Semiconductor refabricated the part, NASA then performed another heavy ion test and no latch up was observed. And so we were able to, or they were able to launch on schedule, which was at the time, it was a big deal. Okay, and this is what the part looks like. Basically, it's an LVDS driver. You got this big old giant drive transistor that was located very close to ground. And it turns out that's where the latch up occurred, was right between the drive transistor and ground. And you can see it identified on this chart. So what they did, they spread these structures apart, and they did some more down below as well, wherever they thought they could, since they had plenty of space, and added okay, they spread it apart, they redesigned it, and you can see it there on the right, the redesigned part. And that's the part that did not latch up, and the device, or the launch proceeded as planned. Now, we eventually published this work back in 2006, but it's a very nice example. SET propagation digital logic. This was also a big deal, and this shows very nicely the utility of the spatial selectivity of the laser technique. Okay, as of 2006, there was a lot of work done on single event transients measurement in inverter chains. Okay, and what they saw was large distribution of pulse width. So shown on this chart, schematically, you see an inverter chain, and at the end, you see a pulse that comes out. Okay, typically they were long, 200, 800 inverters, depending on the technology node. And this is the way the experiment is done. You irradiate at an accelerator. This particular design was set up so that we could measure the fast transients with a single shot oscilloscope. And this is what the result looks like. You get this wide distribution of transients. Now, these transients basically were scary as hell to the industry, because they see these 2 nanosecond transients that they think are propagating around their circuits, and thinking that they have to design around those to mitigate those. So we went in with a laser, and this is what the structure looks like. 4 rows of 200 inverters. You've got your input at the top, your output at the bottom. Okay, and then the 4 red dots show where we injected the laser pulses, okay? And so when we injected right close to the output, as is shown here, you got these very narrow transients. As we moved to the next row, we got broader transients, much broader. The next row, they broadened a little bit. And then near the input, we got these very broad. These were the 2 nanosecond transients that were commonly observed in the heavy ion testing. Okay, and what this told us was that the transient gets broader as it propagates down the inverter chain. And the reason row 3 and 2 are so similar is because the transient is not propagating very far. It's just around that little bend. So it's not going through a lot of inverters. Okay, so this is well, we called that propagation-induced pulse broadening, and it turned out to be a pretty big deal at the time, and this is why. First of all of the existing data had to be pretty much reinterpreted because this effect wasn't understood, and so it had to be reinterpreted in terms of this pulse broadening effect. The big consequence was in terms of SET mitigation approaches. Basically, I remember sitting in a program review once when a program manager recognized that he didn't have to design his circuits to accommodate 2 nanosecond pulses. He only had to deal with 200 picosecond pulses. And he realized immediately how much money that was going to save him once he made that revelation. And what it also did was it changed the way people did test methodologies. Instead of having long chains of reverters, people started testing short chains of reverters in parallel, for example. Because this is it's not a real effect. Well, it's a real effect, but you don't get chains of 800 inverters in real circuits. Typically your inverter depth or your logic depth is no more than 15 or 20. And so you're not going to see these effects in a real circuit, even though they were showing up in test structures. So a lot of lessons learned from this. Analog single event transients. I've already showed the LM124, shown again here. And you've seen what the transients look like, okay? So you can probe all these transistors with a laser. When you do a broad beam heavy ion experiment, you basically hit the whole device at once. You don't know where your transients are originated. We were able to go through using the spatial selectivity laser and pretty much identify all the different transient shapes that were measured in this device, and that's what's shown in this figure. 3D mapping using 2-photon absorption. I showed you this example already. I'm not going to go through that again, but here's an interesting example. This was some early work done back in 2012 by the Puget group. This is looking at the depth dependence, the Z dependence of burnout in a power MOSFET. There's not a lot of information shown here, but these results showed that you could use this technique to evaluate the 3-dimensional sensitivity of burnout in these devices. This work has not really gone very far. We did some experiments recently on some GaN, gallium nitride power devices. I think there's a lot of utility here that has yet to be capitalized on. Screening. Part screening is a big deal. And it's getting to be a bigger deal as accelerator time becomes harder to get. 2 concepts here: screening a part to reject, screening a part to accept. It's important to understand the difference. This is one example we did of screening a part to reject. Basically, in this example, 2 resolver to digital converters. This was done for NASA. The laser permits us to accurately determine the locations of SEU and SEL in this particular device. And the white rectangles show you where we found single event latch up. we were able to push it a little bit further. Oh, well, okay, first this point. The other part was not latch up sensitive. So basically, the point made in the second bullet there is that due to this result alone, NASA eliminated this part from further consideration for that and any future missions. It was just simply not acceptable, and the other part was. Now, we were able to push it a little further and actually get a threshold somewhere around an LET of 8 MeV centimeters squared per milligram, which agreed precisely with the heavy ion data that was available. Now, the heavy ion data doesn't have the precision, so but we were in their range. We were bracketed between 5 and 15. So that was a nice result at the time as well. Okay, screening is routinely used to eliminate parts from consideration. I just showed you an example. Other labs do this as well. However, screening is rarely used for part acceptance. And the reason is, the particle beam, the heavy ion accelerator, is the gold standard, okay? And everybody accepts that. And there's a lot of trepidation about accepting a laser result. Now, this is an active area of research, and we're working towards this. And some very nice results. I think we had some presented at NESREC last year, published in the TNS, and there will be some more this year. Okay. Analog single event transient screening is another area of that's widely utilized. The laser can be used to generate worst case transients for linear devices. We get good agreement between laser and ion pulse shapes. I showed you one of those examples already. And for this V delta T representation, I'll show you one of those in a second. The laser has proven effective and cost efficient for screening these parts. And so several labs are use this routinely. We have parts flying. I can say, I don't mean we, but JPL has used this technique to screen parts for their various missions, and you've all heard about those. Okay, so the V delta T technique. Basically, you measure the transients as a function of position and pulse energy, and you catalog the voltage amplitude, the peak amplitude, and the width, and you plot it as is shown on the right. Peak voltage versus pulse, full width, half maximum. Okay, you do this for the entire device and you get something like this. And how this is used for part screening? Well, basically what it gives you, where the arrow points, those are worst case transients. They're the largest amplitude, fattest transients that you're going to be able to get. You're not going to be able to get any more with any ion that exists in the natural environment. And so designers can take these transients and plug them into their circuits and see what they do, basically. And if it's something that doesn't cause a problem, they're good. If the transients are causing problems downstream, then they can filter them. There are various things they can do. If they can't filter them, they might have to get a new part. But basically, it notifies them that there's a problem. And so that's how this is used. And so these are just some conclusions, basically what I just said. Screening to eliminate parts is fairly common, and it's becoming more common. Screening to accept parts is really an area of active research, and we're working on this. It depends on many things, one of which is the philosophy of the program manager. Okay, quantitative considerations. Let me see. I am just about running out of time, I believe. So this, I'm not going to say much about this, but I'm going to say why we care. Basically, as I've noted, the primary advantage of laser-based SEE approaches lies in their qualitative capabilities, sensitive node identification, RHBD verification, et cetera. Okay, but in order to have reproducibility from experiment to experiment over periods of months and years, you need to be able to characterize where you're performing that experiment. And with two-photon absorption, it gets fairly complicated. you need to be able to monitor that operating point. And we've done a lot of work in recent years to be able to do that. And I'm happy to say that now we can and we do. And it's very important for what we do. And the other area, well, this is the same thing, but quantitative characterization. There's two aspects to this, actually. I just mentioned the first aspect on the right. We need to understand the pulse delivered to the chip. We call that TPA dosimetry, and we can do that now. The other aspect is you really need to understand the nonlinear pulse propagation, and I've talked about that earlier too. So now we pretty much have a complete picture, and we can very well describe what we're seeing and what we're measuring in the device. Okay, so now that we have this, we can really attack the area of laser ion correlation, which is another active area of research. We can do things that we couldn't do previously because we can actually do the measurements correctly. Yeah, that's basically the truth. So I'm not going to say much about this except that it is a challenge. It's a challenge because of technology diversity. We know CMOS, HBT, bulk, epitaxial, SOI, 3-5, heterojunction, FinFET, et cetera. There's a diversity of parts and part types out there, and each one is going to be a little bit different. And that's where we came up with this I call it a sensitive volume line, basically. It plots out the different types of devices, from the very large bulk devices to the very smallest CMOS SOI. And in order to understand laser ion correlation, ideally, you want to understand this entire technology graph. And it's a tremendous challenge. And we've been picking it off and working on it to the best of our ability, and we've done quite well. This shows one example. This is on the bulk end. We've done SOI as well, but you can see laser data on the left for 3 different conditions compared to the ion data on the right, and you can see excellent agreement. So this is a step in the right direction, as I say. And this is for a bulk diode. We can very easily do the SOI end of things too. And the reason is because the sensitive volume is so well defined, we can do simple calculations. It gets more difficult in the middle though, and we're working on that. There's been some nice work done recently, but I don't have time to talk about that today. It's been presented at NESREC in the past few years. But I believe that's basically what I have. I've given you an overview, theoretical basis, a few experimental examples, some historical and some current, and mentioned some things that we're working on now. I did not get to talk about the Axcom-based SEE. I took that out at the last minute because it's not particularly relevant to, I don't think it is maybe to the automotive side of things. It is relevant to the space side, and it's quite exciting, but I'll save that for another talk. Thank you.